Hello, everyone. My name is Breno Miranda. I'm from the Federal University of Pernambuco, and I'll present a work titled Testing Non-Testable Programs Using Association Rules. This is a joint work with Antonio Bertolino, Emilio Cruciani, and Roberto Verdecchia. The problem we address in this work is that of testing non-testable programs. In classic testing, this is what we usually have. We have a program P to be tested, and we would usually be able to determine the expected output of P given an input X. A test case T can then be described as a pair of input X and the expected output of P for that particular input. With that, we can then observe the actual output of P, and if it matches with the expected output, we say that the test case passes. Otherwise, we say that the test case fails. For some programs, however, such a test oracle cannot be determined with a reasonable effort or does not even exist. In a recent software engineering practice paper, John and colleagues noted that some simulation systems constitute the essence of non-testable programs because a test oracle is not only unknown, but inherently unknowable. When testing systems for which an oracle is unknowable, the traditional meaning of test, as presented in the previous slide, is lost, as you cannot always decide whether a test passes or fails. For such systems, we need to reason in different terms. In this work, we reason in terms of plausibility testing. So here we have again the previous slide for traditional testing with just a few adjustments. While we cannot determine the exact expected output behavior of P for input X, we can still, for some cases, have a prediction of the expected output of P given X. If we can do that, then after observing test execution of P, if the actual output matches with the predicted output, we say that the observed output O is plausible. If the actual output does not match with the predicted output, we say that the observed output O is suspicious. In our work, plausibility and suspiciousness are established based on how the system has behaved so far. Here's our idea to approach this problem. We propose an approach called armored testing that mines association rules from which we can derive testing inputs and oracles. Association rules are not a new concept. They were conceived in the early 90s for mining interesting relations in large databases, for example, in market basket analysis, and they have been successfully applied to solve some software engineering problems, from hacking code clones to statically detecting software bugs. The idea behind the armored testing is simple. We mine relevant association rules by observing features and actions of a system while in operation. Then, a mined association rule can be used as a test case specification to test the follow-up behavior of the same system. An association rule expresses an implication such as A implies B, meaning that if we observe A, then it's likely that B will also be observed. The left part of the association rule is taken as a test input, and the right part, the implication, as a test oracle. In this way, armored testing supports automated mining not only of the test oracle, but also of the testing input. Here's an overview of the armored testing process. The preparation phase contains 4 steps. First, by monitoring features and actions of the system in operation, we build a database of observations, each one modeled as a set of items. Then, at step P2, we mine from the database the set of frequent item sets based on some previously defined threshold. At step P3, we generate a set of association rules using the minor frequency item sets. Here at step 3, the number of generated association rules could be very large. So you need to have a way of selecting the relevant ones. Basically what to do is that we make use of well-established metrics from the association rules domain, such as support, confidence, and leverage for selecting relevant rules. Finally, at step P4, we generate a plausibility test suite by mapping rules to test cases. During the testing phase, we start by monitoring the system in operation, and when we observe an input X and its associated output O, we retrieve from the test suite all the tests generated in the preparation phase that have the input X in the row, more precisely in the left part of the row. Then, for each test, the output O is flagged plausible if the expected output is observed in the actual output, or suspicious otherwise. Now I would like to discuss some of the main challenges for putting our approach into practice. We have already identified two main challenges: evolvability and scalability. For the case of evolvability, for ensure that the concept of armored testing can find an application to practical system, we need to allow the concept of plausibility and suspiciousness to evolve, which means that we cannot mine the association rules once and for all during the preparation phase. Instead, they have to be periodically updated according to some policy, and of course, depending on the domain. For scalability, in the worst case scenario, any exact algorithm takes exponential time for the steps P2 and P3 of the preparation phase. In practice, the worst case scenario never happens, which makes the problem tractable when the number of features n is not large. However, for scenarios where the number of features n grow very quickly, some non-trivial adaptations to make our approach work would be required. Application scenarios. We believe armored testing can find application in many different contexts. For the scope of this presentation, we would like to discuss 3 scenarios: regression tests of digital twins, realism of bots for assessing bots' behavior, and detecting abnormal user or community behaviors. These scenarios are conceived in response to a real-world problem for testing large-scale distributed systems. In particular, they were inspired by a request for proposal launched by Facebook to address the challenges of testing agent-based user interaction simulation. However, as you see, they are generic and they could be applied in different contexts. For the regression testing scenario, our assumption is that modification in the real system can be tested in the digital twin before going into production. With that assumption in mind, armored testing could be used first to derive association rules based on the platform functionality that changed or that will be changed. This is the preparation phase. Then, in the testing phase, armored testing could be used to test the digital twin to verify if the mined rules still hold after the modifications. Because of the metrics I mentioned earlier, the mined rules are naturally prioritized. For example, we could prioritize them based on the expected probability that given A, then B is likely to be observed from highest to lowest. This can be useful for guiding the test session. For the scenario on realism of bots, our assumption is that the bots used in the target digital twin are derived from personas modeled from real users. For applying armored testing, first we learn from the real system how typical user interaction patterns are correlated with the user features that were taken into account to create the personas. Then, while running a test session on the digital twin, we could test the bots themselves by checking if the interaction patterns are expected or not, by comparing them with those of the personas they were modeled from. This scenario can be useful because one could define that if a bot starts having too many suspicious behavior, then the test session should be restarted with a new bot, possibly a better one. For the scenario on detecting abnormal user community behaviors, there are two ways in which ARMAD could be applied. If some sort of database of actions that would flag a user as a bad actor is available, then the application would be very straightforward, as we could use ARMAD to derive rules for hinting at abnormal behavior and compare them against the behavior of all the real users. If such a database of abnormal actions does not exist, we could still use ARMAD. During the testing phase, if some unexpected behavior is observed, some behavior that does not match with any of the rules previously mined, that behavior is reported to the tester as an action worth of attention. Future plans. As part of our future work, we plan to associate the concept of ARMAD testing in several testing scenarios in order to evaluate the feasibility, effectiveness, and scalability of the approach. An open question I'd like to also address as part of our future work is whether ARMAD and metamorphic testing could have a useful combination. Thank you for watching.